Hello guys, this is another exciting topic in this course. Let's see what we got. Okay, let's look at our roadmap again and see where we are. Two fundamental topics, formal languages and automata, are done. And in this lecture, we're gonna talk about the theory of computability. This is actually a huge topic, and consider this lecture just as an introduction. Let's get started. Let me review quickly a couple of things to shine our knowledge and make sure that we are on the same page and we are clear about what we need here. The first thing is Turing machines are more powerful than other machines. We have no doubt at this moment. The second thing is we can combine Turing machines to construct more complex Turing machines. And we took some examples during the semester and we are sure about this. And the third thing is problem is equivalent to formal language. And when we say we are solving a problem, first of all, solving, accepting, recognizing, understanding, and even computing, all of them are interchangeable, and it means that we are in fact solving problem because we learned that we can represent every problem with a formal language. The fourth thing is Turing machine is the ultimate computational power we have. We could not construct more powerful than Turing machine yet. As usual, we need to know why this topic is important and why we should learn it. Let's start with this important question. Is there a solution for any problem? Or, in other words, is there any unsolvable problem? To answer this question, we know that this is the set of all formal languages that Turing machine can solve, and we call them Turing recognizable languages. All right. Now, based on this question, I am asking, is there any more? I mean, is there some languages here that is beyond the capability of Turing machines? Okay. Just as an FYI, I'm telling you that there is a theorem that it says the set of all formal languages is bigger than the set of all Turing machines. It means that there are some problems that cannot be solved by the Turing machines. All right. And based on this question and this answer, let's see what is the objective of this lecture. In this lecture, I'm gonna show you that some problems are beyond the limits of computation, and in plain English, I want to show at least one problem that is unsolvable. But before that, let me warn you guys that you are watching this video. To understand all of these materials, you really need 200% attention. So 100% is not enough at all. And also, I am gonna give you this warning that at the end of this lecture, probably you will look like this. So give a heads up to your family. Just joking. Yeah. In this section, I want to introduce a thesis called Turing Thesis. Alan Turing in 1936 gave a conjecture that is known as Turing Thesis. Actually, it is also known as the Church Turing Thesis, but definitely we would prefer to call it Turing Thesis. So he gave us a very high level hint that what kind of problems is computable. Here is the statement of the Turing thesis. Any computation carried out by a mechanical procedure can be performed by a Turing machine. In this statement, everything is fine, everything is clear, except this mechanical procedure. What is the mechanical procedure? So here is the definition. A procedure is called mechanical if this procedure or P has finite number of instructions. So if we are stating an algorithm, the statements of this algorithm should be finite. Second, P produces the result in a finite number of steps. Maybe the number of the instructions are finite, but maybe we have a go-to here, for example. We can create a loop here, right? And the number of the steps should be finite as well. So no infinite loop is accepted. And this procedure P can be carried out by a human being with no specific ingenuity and unaided by any machinery. So any regular person without any special skill should be able to handle that. Okay, so if a procedure has this specification, it is called mechanical procedure, and Turing is saying that this kind of procedures can be handled by a Turing machine. Okay, the point is that we cannot prove Turing thesis, and also we could not refute it yet. Does this look strange? So how come we are using Turing thesis when we cannot prove that? Yeah, that's the problem we have in science, in fact. Exactly the same thing that we cannot prove Newton's laws of motion in physics. We cannot prove them. Are you asking why? Because if we want to prove those laws, then we need to test those laws on all objects in the universe. Can we do that? We cannot do that. Exactly the same thing we have for the Turing thesis. All right. So we say as long as there is no counterexample, we agree that these Newton law are correct and this Turing thesis is correct as well. This is how we behave in the science. Okay? In this section, I want to introduce a cool and very important Turing machine that played a significant role in constructing digital computers. Let's see what it is. Up to this point, all of the Turing machines that we constructed were hardwired. What does it mean? It means that we designed Turing machines specifically for one language. So the Turing machine's job was to accept only one language, right? But the point is, real computers are programmable. It means that we can run many programs inside the operating system of a computer. Now, based on this introduction, is it possible we create a Turing machine that runs other Turing machines? Very cool question, right? The answer is yes, we can do that, and we call it Universal Turing Machine or UTM. Universal Turing Machine is a standard Turing machine. Yeah, I want to emphasize that it is a standard Turing machine. It is a Turing machine like other Turing machines, but we design it in such a way that it can run other Turing machines. It was proposed by Alan Turing in 1936. Again, another genius thing, right? As I explained in the previous slide, to have a clear picture, just imagine it is an OS. So UTM is an OS that can run other Turing machines. Let me be a little bit more specific here. This is our UTM, or Universal Turing Machine. It has two inputs. First, a description of another Turing machine, and the input string of this Turing machine, because we need to run this against this input. If we want to be even more specific here, here is how the tape of the UTM look like. We have the description of a Turing machine here. That is a string. Of course, it should be a string. And we have the input string of this Turing machine. That, of course, it is a string as well. Okay, so we describe our input Turing machine and convert it as a string, and we put it here. And this guy is the input of this Turing machine. So we combine them and we put on the tape of the UTM. And we designed this UTM in such a way that it can read this description, understand it, run it against this input string. Now we encounter another important question. How can we describe a Turing machine as a string? Specifically, I am talking here. So we said that we need to put a description of a Turing machine here in such a way that the UTM can understand that. But how can we do that? This is the topic of our next section, but let me give you some hints here. So you remember that we said a Turing machine can be defined by a septuple, and we have 7 items here. And if we can define them by a string, then it means that we can define the entire Turing machine as a string. And this process is called encoding. Now let's see what is encoding. We all know that the input of Turing machine should be a string. If we have other objects, like for example, we want to work with the graphs or trees or other automata or grammars, you see, none of them are string. So we must convert them to a string. So here is the definition of encoding. The process of converting an object to a string is called encoding. Question: how can we do that? Let me explain it via an example, and just please note that this is just one way of encoding. We have many ways of encoding. We have this Turing machine and we have this string. We want to encode this Turing machine and this string. We already know that we can define mathematically a Turing machine with septuple or 7 items. How can we do that for this machine? For this particular machine, the Q is Q5 and Q2. The alphabet is AB. The gamma is, look at this. So we have B, we have A, and we have blank. So these are all of the alphabets and other symbols that are being used in this Turing machine. What is the initial state? The initial state is Q5. What is the set of the accepting state? We have only one. And what are the sub rules of the transition function? We already know what these are, so we don't need to be worried about the detail of this. Okay, now the question is, how can we encode all of these stuff? We are going to use unary numbers because of their simplicity. For encoding the set of the queues, here is one rule. So the first element is encoded as 1, the second element is encoded as 1, 1, and we can continue this way. So for this example, Q is 1 and 1, 1. So this is actually the Q5, and this is for Q2. For the alphabet, we don't need to encode it independently because always for the Turing machines, the alphabet is a subset of the gamma minus the blank symbol. Okay, so if I encode the gamma, then the alphabet will be encoded automatically. So in the next slide, I am gonna encode the gamma. We use the same policy that we mentioned for the queues. So we encode the first element as 1 and the second element as 1, 1, and so on. For this particular example, as you see, the gamma is encoded something like this. How about the initial state? The initial state, or Q0, in this particular example is Q5, and Q5 has already been encoded when we were encoding the Q, so we don't need to encode it independently. So in this particular example, it is encoded as 1. The set of final states. So again, Q2 was encoded when we were encoding the Q. So the set of the final states here, since we have only one state and it is already been encoded, so we will be using the 1, 1 for this purpose. The only thing that remains here is encoding the movement symbols L and R, because we would need these encoding for encoding the subrules. So yeah, we just encode L as 1 and R as 1, 1. Okay, now the question is how to encode a subrule. As you see, the subrules has this syntax. We need to invent a new syntax for our encoding. We will be using the same syntax here, but we just remove the parentheses and the equal sign, yeah? The only thing that we need to encode is this QI that already has been encoded, and this is the symbols of the gamma. This is Q, symbols of gamma, and the symbols of the movement. All of them have been encoded before. Okay, so we just need to put together all of them. So I encoded the delta as the D, and we don't need these parentheses. The Q5 is already been encoded as 1. We use the 0 for the separator, and the A is 1, 1. Again, 0 for the separator, 1 for the Q5, 1, 1, 1 for the B, 0 separator, and 1, 1 for the movement R. There is another point here that we need to take into the account, and that is Q2, R, and A. In this example, all of them are encoded as 1, 1. How don't we confuse which one is which? Okay, so the answer is their location. Their location is important. For example, here, when I see the D, it means that one subrule is starting from here. And after that, I expect to see a code of a queue, which is the current queue. And after that, this 0 is a separator between the Q and this guy, which I expect to see a symbol from the alphabet or the gamma, right? Again, we have a separator here, that is the separator of the domain side and the range side. And here I expect to see one code for the queue and so on. All right. So bottom line, how can we not being confused between the codes, their location in the syntax? How can we encode the string? Since all of these alphabets have been encoded before, we use whatever we have in the gamma and we'll encode the string. And we put the 0 as the separator. So this is actually the A and this is the B. Okay, now let's put together everything that we said on the UTM's tape. Here is how the tape of the UTM looks like. So from here to here, we have the description of the Turing machine. And from here to here is the string that we want to input to this Turing machine. Okay. And I just mentioned here only one sub rule because I don't have enough room here. Yeah, we can continue the other sub rules here, but the completed code for this example looks like this. All right, so this is the input string, and from here the sub rules start. So we had three sub rules, and as you see up to here, and here is the set of the accepting states. The rest of that, we didn't need to encode them, but it might be different in different encoding systems. All right. Now the question is how UTM works. I'm not gonna go in the details because we are not gonna implement this UTM here. Well, actually, we did before, but in this lecture, we are not gonna do that. So, in a nutshell, your UTM needs to read this string and process this string against this Turing machine. And of course, you need to keep track of the what the current state is, but you have unbounded tape after this and before this. You can specify some portion of that for keeping track of what is the current state. The last question here is how UTM shows the result. So it halts in an accepting state if M accept W. All right. So this UTM finishes its job in an accepting state if this Turing machine accept this string, and it needs to halt in a non-accepting state if M rejects W. And for this example, actually, it should halt in an accepting state because this AB will be accepted by our example Turing machine. Okay, so let me give you some notation here. So the encoded object, we show them like this with angle bracket. And if we want to encode several objects, we will be using this notation. So we just comma separate those encoded things here. For example, the combination of the Turing machine M and the input string W is denoted by this guy. Now let me give you some notes here, very important notes actually. By this technique, we can encode everything, all kinds of the objects. For example, any kind of automata, any kind of number, any kind of polynomials, graphs, grammars, matrices, and so on. We may employ different encoding. This encoding can be a standard encoding, it can be, non-standard. The way that we did is just non-standard encoding, of course. And also, you can use any kind of numbers. For example, we use unary numbers. You can use the binary numbers. All right. But the point is that the result of the computation must be the same. regardless of what encoding you pick. And the last point is the set of all encoded Turing machines is a formal language. What? Yeah, if you can convert any Turing machine, let's say Turing machine 1, you can encode it and create a string for that. Turing machine 2, you can create a string for that. And the set of all of these string itself is a formal language. All right. In this section, we have a sweet topic called decidability. Let's see what it is. We start from the Turing recognizable languages. What was that? A language is called Turing recognizable if we have a Turing machine that recognize it. Okay, so what? Let me deal with it a little bit in detail. A language L is called Turing recognizable if a Turing machine halts in accepting a state to accept the strings of the L. All right. How about the rejection? For the rejection, if we put a string from the L bar on this Turing machine halts in a non-accepting state, or it gets stuck in an infinite loop. So you remember that if the machine is stuck in an infinite loop, we would say that this string was rejected, and this is the root cause of a problem. Why is that? Because we already mentioned this. It is impossible to distinguish whether a machine is in an infinite loop or it is in the middle of a very long computation. So if the machine is in infinite loop, then we really don't know that it is in the middle of a very long computation or it is in an infinite loop. That's the problem. Even though we mentioned that before, but we didn't prove that, and we're gonna prove this in this lecture. All right. So because of this ambiguity that could happen, we prefer Turing machines that always halt on all inputs. All right. So if this is the case, then we need to separate these Turing machines. How? We define a new groups of the Turing machines and we call them decider. So a decider is a Turing machine that halts for accepting or rejecting. So if we say that this Turing machine is a decider, it means that it always halts and we are sure that this Turing machine never gets stuck in an infinite loop. In other words, they always can make a decision clearly, all right? And a language is called Turing decidable or simply just decidable if there is a decider for it. Okay, so now let's look at our hierarchy of the languages one more time because we created a new groups of the Turing machines. As you see, we separated this Turing recognizable from the Turing decidable. All right. So if a language is here, it means that there is a decider for that, and decider is a Turing machine that always halts. But if there is a language here, it might get stuck into an infinite loop. All right, so that's the difference between these two languages. Now we need to take some examples. Look at this language. We define a language whose pattern is encoded string. We have a machine here and we have a string here, and this string is in fact the input of this machine. All right. The machine M is DFA and W is the string that this DFA accepts. Like the examples I took when I was talking about the encoding, but now here we have DFA instead of the Turing machines. We can define this DFA as a string like exactly the way that we define the Turing machine, and we can encode this and put it here. So we will have a string, the description of the DFA and the encoded string W. You see, we can convert everything to a string. All right. So we have a language whose strings looks like this. So this is a language, in fact. Now the question is this language decidable? What does it mean? It means that can we create a Turing machine that accept this kind of language? If this Turing machine is going to understand these strings, it should be able to simulate this machine against this W. Okay, so we have to encode the DFAs and we have to encode the strings and we have to create a Turing machine that can simulate the operation of this machine against this string. Now the question is, if we create this Turing machine, is it a decider or a regular Turing machine? So I would say this Turing machine will be decider. How am I sure that this Turing machine does not get stuck in an infinite loop? That's a very good question, right? Because I know that DFA never gets stuck in an infinite loop, right? Since DFAs do not do that, it means that the Turing machine that simulates this operation should not get stuck in an infinite loop too. Of course, we assume that we designed this Turing machine correctly. One more time, since DFA never gets stuck in an infinite loop, the Turing machine that simulate it, it shouldn't get stuck in an infinite loop too. So with 100% certainty, I would say this is a decidable language. It means that there is a decider for that. The next example is this. We have the same type of the language, but instead of the DFA, we have regex here. The question is it a decidable language, or can we create a decider for this, or can we create a Turing machine that simulate these regex against this string? The answer is still yes, because we have a theorem that converts regex to NFA, and we have a theorem that converts NFA to DFA. And as you see, with these two theorems, this language will be converted to the previous example, all right? And since we answered yes to the previous one, with these two theorems, we can say yes, for this language, there is a decider. Now we want to simulate a Turing machine. So this machine is a Turing machine and this W is just a regular string. Now we are asking the same question. Is this language a decidable language? In this case, we would say no, it is not. Because Turing machine has the potential to get stuck in an infinite loop. Okay, and if we create a UTM for that to simulate this language, as we explained when we were talking about the universal Turing machine, then since this Turing machine can get stuck in an infinite loop, so as this UTM. So The answer would be no. This is not a decidable language. Okay, now let me explain it in detail. Maybe this example was not so clear. All right, so this UTM is simulating M against W, right? There are three possibilities. M accepts W and halts. In this case, UTM halts in an accepting state. So remember that UTM is the machine that simulates the operation of this machine. So in this case, the UTM halts in an accepting state. Second possibility is M rejects W. In this case, the UTM halts in a non-accepting state. So this is the first kind of rejection, that machine really halts in a non-accepting state. So in this case, the UTM should halt too. But the third possibility is M reject W, but in this case, it falls into an infinite loop. And since this machine falls in an infinite loop, the UTM that is simulating that operation should fall into an infinite loop too, right? And this is the problem. So this UTM, since there is a potential situation that it can get stuck in an infinite loop, then we would say, hey, this UTM is not a decider. But the language, of course, is Turing recognizable, but it is not decidable. In this section, we want to talk about one of the most important and one of the most famous problem in computer science that is called halting problem. This is actually a theorem that shows the limitations of computation. As we said before, computer, like any other tools, it has their own capabilities and limitations. And this problem, or let's say this theorem, shows one of them. This theorem actually was introduced by Alan Turing in 1936. It was introduced and proved. But to understand this, we need some warm up. Okay, we start from this weird game. This game can be played by one, two, or more players. It has two simple rules. The first rule is you need to move if you see a still person, and you need to stop if you see a moving person. Now, we want to play it alone. Stand in front of a mirror, look at yourself, and start playing the game. Will you move or stop? Very weird, right? Because right after you want to move, you need to stop. And when you stop, you need to move. Another paradox is the barber paradox. It's a very famous paradox. Let's say there is an isolated village with only one male barber. In this village, there are two very strict rules. If someone does not shave himself, the barber shaves him. Let's call them group A. And the rule number two is if someone shaves himself, the barber does not shave him. So this is group B. Okay? Now the important question, does the barber shave himself? When the barber starts shaving, he falls into group B, the people who shave themselves. So he should stop shaving. And when he stops shaving, he falls into group A and he should shave himself. And this is a paradox. Another one. This is actually a classical paradox. Is this true or false statement? This statement. This statement is false. Is it true or false? Again, we have two possibilities. If we say this is true, then it should be false because the statement itself is saying that I am false. But if we say no, that was not true, okay, so it is false, then what would happen? Its negation is true. So the negation of the P will be true. What is the negation of the P? This statement is true. So it should be true. You see? When you start from here, you reach here. And when you start from here, you reach here. And this is a paradox. This one is the coolest one. It is called Bertrand Russell's paradox. So he introduced the following set. All sets that do not contain themselves. What does it mean? We are talking about a set, and we call it R because of the Russell. And this set contains all sets. So the members of this set are sets. Okay, all sets that do not contain themselves. What is the meaning of this? Yeah, first we need to understand clearly what the meaning of this sentence is. So we know that the members of these sets are sets. But what kind of sets? The sets that do not contain themselves. What does it mean? For example, if this is A, and if, let's say this is B, and A and B and many other sets belongs to this, their specification or their property is that they do not contain themselves. So for example, here we don't have A here. Maybe it has many other elements. Maybe one of them is A, but if it does not A as a member, it belongs to this set. Yeah, yes, let's take some examples to understand fully what the meaning of this sentence is. All right, so let me start with a simple set. The set of all pens in the world. Here is the set builder of this set. X such that X is a pen. So if X is a pen, it belongs to this set. So in fact, if I want to enumerate this, so let's say a pen 1, pen 2, yeah, your pen in your pocket is, let's say, pen 3. Yeah, you see, all of the pens in the world belongs to this set. Now the question is, does A contain A? In other words, does A contain itself? It means that if I enumerate this as I did, pen number 1, pen number 2, and blah blah, is A here? A is part of these sets? Of course not, because A is not a pen, right? A is a set of the, all of the pens. So since A is not pen, so it does not belong to the A. So these kind of sets are those that they do not contain themselves. So A is not a member of A. All right. To clarify this, let me take another example. The set of all non-pens. If everything is non-pen, we collect them in this set. For example, cars. Yeah, car 1 is a non-pen, right? Car 2 and all of the other cars. And then let's say balls. Ball 1, ball 2, all of the balls are non-pen. Okay, now the question is, does B contain itself? In this case, we would say yes, because B is a set of something, right? And it is non-pen. So do you agree that B is a non-pen, right? So this sets as an infinite set, and it contains anything that is not pen, and B is one of them. So we would say B belongs to itself. All right, now let's get back to the Russell paradox and try to understand the set that it is talking about. So before going there, we just need to focus on this one, the set that does not contain itself, right? Russell's set is talking about a set like this guy, the sets that do not contain themselves. So you can imagine Russell's set as something like this. You know, the members look like this A, the set, let's say the set of all pens, the set of all cars, the set of all balls, the set of all chords, the set of all everything that do not contain themselves. Now we have a very good understanding about what set this Russell set is. Okay, so and here is the set builder version of the same set. R is equal to X such that X is a set. So all of these members are set. You remember that. And then X does not belong to itself. Okay, now that we have a clear understanding what set it is, now the important question, does R contain itself? What does it mean? It means that can one of these members be R? So can I put R here? R contains itself? All right. The dilemma starts here. Why? Because if I put R here, then R contains itself and it is violating this rule. So we need to remove that. And if we remove this R, then it means that R has this property that it does not contain itself. Then I should return it back here. And this is a paradox. And just as an FYI, these sets, when it was introduced by Bertrand Russell, ruined the set theory. They had to redefine the set theory. Okay, what is happening here? In all of these examples that I just show you, something was referring to itself. And that's why we call these kind of paradoxes self-referential paradox. Okay? As a rough conclusion, let me tell you this statement. If you have a statement and something is referring to itself, most likely a trouble will arise. I think we are warm enough to talk about the halting problem. Okay, so what is the halting problem statement? We have a language, let's call it L halt. We are already familiar with the meaning of this. It is the encoded version of a Turing machine M and a string. The combination of this string and the description of a Turing machine, but the property of this Turing machine and this string is that this Turing machine will halt when we feed this string. So when we say it halts, it means that it doesn't fall into a infinite loop. For sure, we know that it will halt either for accepting or for rejecting. Okay? Really, first we need to understand clearly what members this language has. So one more time, all of the members of this language are strings that has two parts. One part is the description of a Turing machine, and one part is the string that we feed into this Turing machine. So this is a description that is encoded of a Turing machine. And what is the property of this Turing machine and this string? For sure, we know that if we feed this string to this Turing machine will halt, either for rejecting or for accepting. We don't care about that. The halting is our concern here. We are sure that this Turing machine will halt. Now, how many Turing machine we can have? Well, of course, infinite. How many string can we have? Again, infinite. So this is an infinite language. Now the important question, is there a decider for L halt? Is there a decider? Decider, we know that's a Turing machine. Can we create a Turing machine that accepts this language? And of course, it needs to halt because it's a decider. Yeah, it does not fall into an infinite loop. Yeah, let's call it decider or whatever. Yeah, we call it H. I emphasize here that we are looking for a Turing machine. Here I called it H because of the halt. Yeah. And this H can decide whether an arbitrary Turing machine, this guy, will halt on an arbitrary string W, this guy. So this arbitrary is important to show you that it can be any Turing machine. The Turing machine H's job is to decide about this language. Okay, so to visualize what I am talking about, so this is the halt tester, or the H is a Turing machine, and its input is a combination of the description of the M and a description, actually the string of the W. And this Turing machine can decide whether this input Turing machine will halt against this W or not. So we can have two messages, halt message or loop message. And when we say message, this halt guy, it can be just as simple as a accepting state. The loop message can be as simple as a regular state. So if it accepts, it means that it halts, and if it rejects, then it means that this Turing machine will loop against this string. Okay, so now we are clear about what are the elements of our proof. Okay, so this was actually a theorem that Alan Turing stated and proved that H cannot exist. Let's go over this proof and see how beautifully he proved this theorem. We use proof by contradiction. We assume H exists. Now, since this is the case that any arbitrary Turing machine against any arbitrary string can be fed into this Turing machine H, then intentionally we try to create a special Turing machine and a special string, and we want to combine both of them and then feed into this Turing machine and show that this is a contradiction. I mean, this H cannot exist because it cannot behave correctly on at least one Turing machine that we created. What are we talking about? Let's construct a test case first. It's just a Turing machine, special Turing machine. First of all, I create a copy of the H, and let's call it H prime. And since H prime and H are the same, or they are a true copy of each other, then their behavior, of course, is the same. And then I negate the output of this by putting an artificial infinite loop after this halt message. So as I said, it was just an accepting state, right? We make it as a regular state, and then we create a infinite loop here. So this is, let's say, it's a small Turing machine whose job is just following an infinite loop. I add it after this state. I negate this one as well. How can I do that? It was a regular state. I just make it as an accepting state. So, in fact, if the machine H prime, which is equivalent to H, halts in an accepting state, now it goes to an artificial infinite loop. And if it shows the loop message or it goes here, then we turn it to an accepting state and it will be accepted. So in fact, we negated these two outputs. We are not done yet with our test case. We create one small Turing machine whose job is to copy whatever we feed it. So if, for example, we feed it a W, it create WW. And then the output of this machine, a small Turing machine that we call it copy and combine, goes to feed into this halt tester H prime. And we put all of them inside a box. And since this is a Turing machine, actually combination of one here, and one here. Yeah, so we have some modification and we added some combined some other Turing machines. And if we put this inside the box, the result will be a new Turing machine. Let's call it X. Okay, so this is our test case. So what was our assumption? The H exists and it can decide about any arbitrary Turing machine against any arbitrary string. All right, X is a Turing machine. What do you think that the H, our original decider, will react against the X? If I encode the X and put it here as the Turing machine, M, and also as the string W, because X, when we encode it, it's just a string, right? So I can put it here as the M, I can put it here as the W. What do you think this H answer to these test cases that we created? Do you think that it goes to halt or it goes to the loop? I want to show you that it goes to a contradiction. How come? Because there are two possibilities, two possible answer for H. Either you can say, okay, so I guess X against X, this H will decide it will halt. Or you can say, no, I say H will show you that there is a loop. We have only two possibilities. Turing machine X halts on input string X. This is the first possibility. And if this is the case, then H should show the halt message. Another one is Turing machine X loops on input string X. And in this case, H should show the loop message, this guy. We want to show that in both cases, it goes to a contradiction. How can we verify H's response? The best way is to verify it via the Turing machine X. What do I mean? Yeah, look at this. It is saying that Turing machine X halts on input string X. All right. So I input the encoded X to Turing machine X and let's see how it reacts. All right. Yeah, let's verify one by one. In the case one, we said that H responded Turing machine X halts on input string X. This is our Turing machine X. Just focus on this, that H responded this. And H is equivalent to H prime, right? This guy. All right. If H responded that Turing machine X halts on input string X, we put X here, actually the definition of the X or the encoded version of the X. The X is this guy, right? Yeah, it's a Turing machine and we can encode it. All right, and we put the encoded string here and let's see what would happen. Based on whatever we said before, this part will create XX and it will be inputted to H prime. And since H prime is a copy of the H, so we expect that it respond exactly as the H. And H responded that Turing machine X halts on input string X. All right, so we have X and X here. And based on this statement, H prime should behave exactly the same way. So it halts, it goes that way. But it goes here and will get stuck in an infinite loop. So do you agree that H was wrong? Because H said Turing machine X halts on input string X. But now we see that it goes here and it will fall into an infinite loop. So in this case, H was wrong. Now the second case. Case number 2, H responded Turing machine X loops on input string X. Okay, so please note that we are using this fact that this H and this H prime are equivalent. And when we say H responded to this, then H prime should behave exactly the same thing, right? And since we negated intentionally, we negated the output of the H prime here, in both cases, the response will be different and it will be wrong. All right. So in this case, H responded this, Turing machine X loops on input string X. Yeah. So we encode the X, this guy, and we put it here. It will be copied and combined here, and it goes here. And since H prime is exactly equal to H prime should respond the same thing, right? Turing machine X loops on input string. So definitely H prime should go this way. And since intentionally we created this halt, so again H was wrong because it said that it will show the loop message, but now it is halting. All right. So here is the conclusion. In the first case, Turing machine X halts on string X. We concluded that Turing machine X loops on string X. And Turing machine X loops on string X. We concluded that Turing machine X halts on string X. Both cases led to contradiction. Okay, so who should we blame? Our assumption, H cannot exist. All right, I'm gonna stop here. See you guys in the next video.